Okay, we're going to go through this handout here called Cellular Respiration ATP Accounting. You're going to have an assignment that's very similar to this, so we'll just structure this video so that you kind of have that in your mind before you move to do that assignment. So the question here is, if 5 molecules of G3P enter glycolysis, how many ATP will be made via cellular respiration? Complete the accounting template below to determine your answer. So let's just jump in and try to do that, starting with glycolysis. So you're asked here, how many NADH are made? How many ATP are made by substrate level phosphorylation? So when we jump to glycolysis here, you notice that 1 G3P will do reaction 6 to 10 once. 2 G3Ps will do reaction 6 to 10 twice, here and here. So that means 5 molecules of G3P will do these reactions 6 to 10 5 times. And what do we make in those reactions? We make 1 NADH and 2 ATP. So when we go back here, 1 NADH times 5 will give us the 5 NADHs. Again, we make 2 ATP in reaction 6 to 10. Again, that's going to happen 5 times with 5 G3Ps, so times 5. And we can carry this ATP over to here, okay, and just say, okay, there are 10 ATP being made there. We'll come to the NADH that's being processed by the electron transport chain, to make the ATP soon enough. So let's jump to pyruvate oxidation. How many NADHs do you make there? So when we look at pyruvate oxidation, you'll notice that pyruvate will go through 3 steps to make acetyl coenzyme A. One of the products of that is NADH. So 1 pyruvate will go through these steps and make 1 NADH. Well, if we're inputting 5 G3Ps, how many pyruvates do we make? Well, we make 5 pyruvates. So that means we're going to do pyruvate oxidation 5 times. So that means we're going to make 5 NADHs. So we go back here, we can put down 1 NADH per pyruvate oxidation step. But again, if we're inputting 5 pyruvates via the 5 G3Ps that were inputted into glycolysis, we have to multiply that by 5. Okay, and again, there isn't any substrate level phosphorylation of ADP to make ATP in pyruvate oxidation, so we're just going to jump now to the Krebs cycle. Alright, so again, we have to look at NADH, FADH2, as well as ATP made by substrate level phosphorylation. Now remember, we had 5 G3Ps, that means we have 5 pyruvates, and then when we finish pyruvate oxidation, we're going to have 5 acetyl coenzyme A's. So that means 5 acetyl coenzyme A's are going to go into the Krebs cycle. When we jump to the Krebs cycle, if 1 acetyl coenzyme A does all of this, we're going to do all of these things, these 8 reactions, we're going to do them 5 times because we have 5 acetyl coenzyme A's. So 5 acetyl coenzyme A's will come in and do those 8 reactions of the Krebs cycle 5 times. So everything that we produce in the Krebs cycle is going to be multiplied by 5. So with 1 turn of the Krebs cycle from 1 acetyl coenzyme A, we'll make 1, 2, 3 NADHs. That's 3 NADHs. So 3, but again, we're going to turn 5 times because of the 5 acetyl coenzyme A's times 5. Go back to the Krebs cycle. How many FADH2s do we make? Well, we make 1 per turn. But again, we're going to turn 5 times because of the 5 acetyl coenzyme A's. And so when we go back to the handout, we're going to put down 1 per turn, but there's going to be 5 turns. How about ATP by substrate level phosphorylation? When we look at the Krebs cycle here, you notice that we make ATP right here, just 1 per turn. Okay, so we'll go to the handout, 1 per turn. So again, we're going to turn 5 times. That's going to give us a total of 5 ATP being made there. Now, we need to jump to the electron transport chain here, because that NADH that's made in the stages of cellular respiration as well as FADH2 are going to be used to make ATP. So based on the diagram and what we've been talking about in class, we're going to say that NADH is going to pump 1, 2, 3 hydrogens, and each of those hydrogens are going to pass through to make 1 ATP. So NADH will pump 1, 2, 3 hydrogens, or protons, hydrogen ions. Each of them will pass through to make 1 ATP, so that means 1 NADH will make 3 ATP. Okay, so when we go back to the handout, right here, we can see that these 5 NADHs here are going to be multiplied by 3, and we're going to get 15 ATP out of those. Sorry, let's back up. I apologize. Normally that's what happens, but remember, NADH in glycolysis is made outside of the mitochondria. So that NADH has to be converted to FADH2 and then moved into the mitochondria. So technically, this NADH here is going to be converted to FADH2, which only makes 2 ATP. Okay, so I'll come back and show you that here in just a second. So 5 times 2 is going to give us 10. Okay, so let's actually, since we mentioned it, let's just jump back and see that. FADH2, you notice here, drops off its electrons at ubiquinone. It completely skips that first molecule, NADH dehydrogenase. So technically, FADH2 is only pumping 1, 2 protons, and if each of them make an ATP, we're going to make 2 ATPs from the FADH2. All right, so we go back to the handout. Again, that's why it's 5 times 2 equals 10. Okay, the NADH made improved oxidation. Again, that's happening inside the mitochondria. They're going to pump 3 protons, and we're going to get 1 ATP per proton, and that's going to give us 5 times 3, which is 15 ATP. Same thing for the Krebs cycle. We get 15 right here. NADH is being made because of 5 turns of the Krebs cycle, but that's going to be multiplied by 3 ATP, and so that gives us 45. The FADH2 here, again, is only going to pump 2 protons into the, by the electron transport chain, sorry, is only going to pump 2 protons, and we're only going to get 1 ATP per proton, so 5 times 2 will give us 10. And then, of course, the ATP that's here gets carried over. So all we have to do now is add all this up. Okay, so 10 ATP here plus 10 there gives us 20, plus 15 is 35, plus the 45 is, sorry, I'm having a bit of a brain fart there. Let's see here. So 10 and 10 is 20, 35, and that gives us 80, plus 10 gives us 90, plus 5 gives us 95 total ATP. Sorry about the little mix up there. So hopefully this will help you with your assignment.